This video begins the discussion of the various design aspects of a cache system. Further aspects of design are continued in subsequent videos. Let us begin by defining some terms which we will be using throughout our discussion of the cache system. This diagram here shows the mental picture you should have while talking about cache systems. There is a processor, and in between the processor and the main memory there is a cache which is typically smaller in size than the main memory. Now in this context, what is going to be the unit of transfer of data between the processor and the cache? For the MIPS architecture, the unit of transfer of data between the processor and the cache is going to be one word or 32 bits. The unit of transfer between the cache and the main memory is typically more than one word. It can be one word also. There is a specific name for this unit of data transfer between the cache and the main memory, and the name is a block or line of cache. When the processor finds what it is looking for from the main memory in the cache, this is known as a cache hit. The required word is found in the cache. On the other hand, if the required word is not found in the cache, that is known as a cache miss. Typically, when there is a cache miss, that corresponding block or line of cache has to be loaded from main memory onto the cache. Corresponding to hits and misses, we have the hit ratio, which is nothing but the number of hits to the total number of accesses, and the miss ratio, which is the total number of misses to the number of accesses. Just to check if you are paying attention, what do you think is the relation between hit ratio and miss ratio? Since each access can either be a hit or a miss, the hit ratio and miss ratio should add up to 1. Hit ratio and miss ratio are two cache performance related terms. Two other cache performance related terms are the hit time and the miss penalty. The hit time is nothing but the time taken to access memory during a cache hit. In other words, this is the time taken to access the cache itself by the processor. Miss penalty, on the other hand, is the time spent during a cache miss. And as I said, typically this miss penalty will involve time to fetch a block of cache from the main memory. Let's begin our discussion of cache design by looking at the simplest possible cache design, where we are going to assume that the block size is a single word. In this diagram, we have the cache on the left side. In this example, I have assumed that the cache is of 8 words size, and the memory is shown on the right hand side of this figure. Only the bottom 16 words of the memory are shown. In this simplest design, what we are going to do is, given a memory word address, we are going to say that the block number in cache corresponding to that word address is going to be nothing but the memory word number, which is the same as the memory block number, modulo the number of blocks in cache. In this example, since the cache size is of 8 words, every 8th word in memory is going to map to the same block in cache. So for example, memory word number 0 and memory word number 8 will potentially reside, of course not both at the same time, will both reside in the cache block number 0. Likewise, memory word number 1 and memory word number 9, both of them map onto cache block number 1. This scheme of arranging a cache where only one cache location is available for a given memory word is known as direct mapped. This is because there is a direct mapping from the given memory word address to the location in cache where that particular word can potentially be found. That is, during cache hits, there is exactly one cache location from where a particular memory word will be served to the processor. Although in theory this is not necessary, in practice the number of blocks in cache is typically arranged to be a power of 2. so that the modulo operation is a simple extraction of few bits of the memory word address. In this example, can you tell which bits of the memory word address will give you the cache block number? Since the cache size is 8 words, in this case, the last 3 bits of the memory word address are going to give the corresponding block location in cache. Let us understand direct mapped caches better with a numeric example. Let us say that we have memory which has a size of 2 power 6 words and a cache with a size of 2 power 3 words. How many bits is it going to take to represent a memory byte address? Memory byte address, it is going to take 8 bits, since memory word address is going to take 6 bits. Let's say we number these bits 0 to 7 starting from LSB to MSB. Which bits are going to correspond to the cache block number? Here are the 8 bits of memory. The MSB 6 bits correspond to the word address, of which the last 3 bits correspond to the block number in cache. The next 3 bits represents the fact that there are 2 power 3 possible words in memory which can all map to the same block in cache. So any of these possible 8 words can be there in each particular cache location. Given this, what do you think is going to be the number of possible states of a cache block? The number of states is going to be 2 power 3 plus 1. This is because a cache block can have one of 8 possible words from memory, or it can be invalid. Typically, the first time a program starts executing, all the cache locations will be invalid because the entire program is only in main memory and no cache location has anything to begin with. At any point, the cache system needs to know in which of the possible 2 power 3 plus 1 states it is in. For this, corresponding to each cache block, in addition to the data itself or instruction, there is the following cache related metadata which is maintained. There is one bit which tells whether or not that particular cache block has valid data, and in case it is valid, there will be 3 bits of tag which will tell which of the 8 possible memory blocks is in the cache currently. Notice that for a given cache block location, the memory addresses, the 8 possible memory addresses which map to that particular cache location, can only differ in these 3 bits, in the MSB 3 bits. And these MSB 3 bits are known as the tag corresponding to this particular memory address. In this cache design, let us now see what exactly happens on a memory read by the processor. The first thing done is, given the memory address which the processor is trying to access, we will find the corresponding cache block using the algebra given earlier. That is, cache block number is nothing but the memory block number modulo the number of blocks in the cache. Having identified the cache block where that memory address could potentially be present, rather the data corresponding to that memory address could potentially be present, we have to check whether the data is indeed present, and the way to check that is the following. We have to use the metadata bits corresponding to that cache block and first check whether the valid metadata bit is set. This will indicate that that particular cache block indeed has valid data. After having confirmed that it has valid data, we have to check whether the tag of the cache, that is the tag maintained as part of the metadata of the cache block, matches the tag field of the memory address. If they match, this is an indication that the data in the cache is indeed data which is actually present in that particular memory address in main memory. So in this case, we have a cache hit which means that we can read that particular memory address which the processor is trying to access from the cache. On the other hand, if the earlier condition check fails, that is, if the valid bit is not set or if the cache tag is not matching, that means that that particular cache block is not having the data that we are looking for. This is an indication of cache miss, in which case we need to load the appropriate block from memory onto that particular cache block and then go back to the case of cache hit. Now, during a cache miss, this process of loading the appropriate block from memory onto cache corresponds to the miss penalty, and during this time the processor will potentially stall. Since this miss penalty involves accessing main memory, which we know is much slower than the cache memory, this can involve several cycles or several tens of cycles of processor stall. All of this functionality of finding the cache block number and checking the cache metadata and loading the appropriate block from memory on a cache miss, all of that is implemented by a module known as the cache controller. We just looked at what happens on a read. This was deliberate because what happens on a write requires more discussion, which we will do later. Having looked at direct mapped cache with single word per block, we can now look at a slight modification to this scheme where we support multiple words per block. In this diagram, I have again shown a cache with 8 blocks, but this time each of the 8 blocks is going to have 2 words in this example. Now, why do you think you might want to have multiple words per block? If you think about it, you will realize that in order to take advantage of spatial locality in the programs which are running, we need to have multiple words per block. Recall that block is a unit of transfer between cache and main memory. So on a miss, when we are loading a block from main memory onto cache, then we will be loading the entire block of memory onto cache. So this then has the potential to take advantage of spatial locality. So for example, during sequential instruction execution, if one instruction causes a miss in the cache, then in handling that miss, the next instruction, which is also part of the same block, will be loaded onto the cache, and hence the next instruction, when it is executed, it will face a cache hit in the instruction access. What we do during a memory access, during a memory read specifically, is going to change only slightly from earlier. Earlier, when we had only one word per block, given the word address, we simply extracted the last few bits of the given memory address as the block number in the cache. In this case, when we have multiple words per block, we are going to have the last few bits of the memory word address corresponding to the word number in the block, and the next few bits will correspond to the block number in cache, and the remaining MSB bits are going to correspond to the tag. So in this example scenario, can you tell which bits of the given memory address are going to correspond to the word number in block? Since in this example we have 2 words per block, we only need 1 bit for the word number in block. How many bits are we going to need for the block number in cache? Since we have 8 blocks in the cache, just like earlier, we're going to need 3 bits for the block number in cache. How many bits are going to be needed for the tag? Well, the answer to that will depend on the size of the memory, which in turn will determine the size of the memory address, the number of bits in the memory address. And just like by convention, the cache size is a power of 2 in terms of number of blocks, the number of words in a block is also typically a power of 2. This will enable easy computation of these fields given the memory address. To understand this better, let us work out a numeric example. Let's say that main memory in a system is of 32 megabyte size and the system has a cache which is of 512 kilobytes, and the cache system employs a block of size 16 words. In this scenario, draw the various fields of the memory address as interpreted by the cache controller. Given a memory address which is word aligned, the last 2 bits will be 0. The next 4 bits will be used to represent the word number in block because the block size is of 16 words, which is 2 power 4. The next set of bits from the LSB are going to represent the block number in cache. To determine how many bits is required for this, we essentially need to count the number of blocks in the cache. So let us do that. Cache size is 512 kilobytes divided by block size, which is 16 words. This will give us the number of blocks in the cache. We need to be careful here because the numerator is in bytes and the denominator is in words. So if you do the arithmetic, this is 2 power 19 bytes and this is 2 power 6 bytes. So this ratio corresponds to 2 power 13, which is the number of blocks in the cache. So we need 13 bits to represent the block number in cache. The overall memory address size in this case is 25 bits because the main memory size is 32 megabytes. So we realize that there are remaining 6 bits after the block number in cache. These MSB bits will correspond to the tag, the cache tag field. Now for this cache, how many bits of memory is it going to take to implement the cache, including the metadata? Well, it is going to take 512 kilobytes for the data itself, and corresponding to each of the 2 power 13 blocks, we are going to have 6 bits of tag and 1 bit of valid versus invalid. So this is the total number of bits in the cache, including the cache metadata. Next, let us look at a cache in action through an example. Here I have taken the same cache as earlier, where we had 8 cache blocks, each of 2 words. And let us say that the processor accesses the following main memory word addresses. This is the sequence of word addresses accessed by the processor. In this case, let us walk through the cache state as the processor accesses these word addresses. When the processor first accesses word number 0 corresponds to block number 0. To begin with, the cache is empty, so this will be a cache miss. As part of handling this cache miss, the cache controller will pull in words 0 and 1 onto block number 0 in the cache. So during access of 0, it is a miss and 0 and 1 are loaded. Following that, during access of memory word address number 1, it is going to be a hit because of spatial locality. 1 was already fetched during the last miss. What about while accessing memory word address 20? In this case, if you write out the binary for 20, it will be 10100. This LSB bit here will be used to represent the word number within a block. The next 2 bits will correspond to block number in cache. So this block number is 2. So 20 will map here. And while pulling in 20, 21 will also be pulled into cache. So 20 itself will correspond to a miss. Next access is for word address number 19. 19 in binary is 10011. Here too, the last bit will correspond to word number within a block, and the next 2 bits will correspond to block number in cache. This is block number 1. So 19 will come here. While pulling in 19, 18 will also be pulled in, which is part of the same block. So 19 will also correspond to a miss. Next is word address number 17, which in binary is 10001. Last bit corresponds to word number in block. Next two bits correspond to block number in cache. Here we see that block number 0 is what word address 17 maps to. Well, 17 is not in this particular cache block. Something else is there. We have to evict it. We are going to now throw this away and bring in 17, and 16 will also come in, and 17 will also be a cache miss. Next, the processor is accessing word number 0. Well, just like what happened earlier, we map word address number 0 to block number 0. But here, unfortunately, the earlier access has evicted 0 from the cache. So 0 is no longer in the cache. So this is also going to be a miss. Now 16 and 17 will be evicted from block number 0, and 0 and 1 will be brought in their place again. So far we have discussed how a cache comes into play during memory reads. Now let us see how cache comes into play during memory writes. It turns out there are several design options here. There are two possible design options corresponding to how we answer this question of what happens on a write hit. One way to handle a write hit is known as write back. Under this option, the processor is going to write only to the cache, and this block of memory will be written back to the main memory later. When exactly will it be written back? It will be written back at the time that particular block is evicted from memory, like it happened in the previous example we worked out. A couple of times a block of memory was evicted to make place for another word address location. So we are going to postpone the write to the memory, to the main memory, to a point where it is absolutely necessary. That is when that block of cache is going to be evicted from the cache. Until then, we can keep writing only to the cache memory. One simple bit of optimization here is that a block of cache needs to be written back to main memory only if it is dirty. That is, it has been written since the time it was brought from main memory to cache. To track this, we need one bit of information. This can be added to the set of bits which are kept as part of a cache block, as part of the cache metadata. The other option is to write through. That is, instead of postponing the write operation, we are going to write that word to main memory right away. Of course, we also need to write that word to cache memory. This is because there can be a read operation in the near future. Since we have a main memory operation in this scheme, in this write through scheme, this writing operation can be quite slow. One idea here to save some time is to have what is known as a write buffer. So as part of the cache controller module, we have a small buffer of words. The processor itself will write to the write buffer and proceed. The cache controller then has the responsibility of reflecting whatever is in the write buffer to the correct location in main memory later on. This idea will mask some of the delay experienced by the processor, and the processor itself can continue. Of course, we will have a problem if the processor is executing a program which has a sequence of writes close to one another, such that the number of locations available in this write buffer is not sufficient. And because of this, delay will surface and will be experienced by the processor. With respect to write hit, here are a couple of remarks on performance. First is, when we use the write back scheme, even a write hit can take 2 cycles. That is, 2 accesses to the cache. The first access will be to read the tag, and only when the tag matches, the actual write can happen. So even in the case of a cache hit, the processor may have to wait until the tag is read, matched, and the actual data written. In order to mask this latency, just like in the write through scheme, we can use a store buffer so that the processor can write to this buffer and proceed with its further instructions while the cache controller does the actual write back. Another instance where a buffer comes of use in the write back scheme is to reduce the miss penalty. We will be able to make better sense of this remark once we have looked at what happens in the case of a write miss. But irrespective of whether we use a store buffer or a write buffer to mask latency during write hit or write miss, we must be sure to check on one thing. On a read miss, we must make sure to check the store buffer and the write buffer, whichever may exist. Otherwise, we will run into the danger of fetching an old value from the memory location onto the cache memory. Just like we had two choices with respect to what we do during a write hit, there are two choices with respect to what we do on a write miss. On a write miss, we can either allocate the block corresponding to the word which we missed in the cache, or we can choose not to allocate. So these are the two design choices. Putting together the two design choices with respect to write hit and the two design choices with respect to write miss, we have overall 4 design choices, 2 cross 2. This diagram represents that. The two choices along the columns are the choices for what we do during a write hit, and the two choices along the rows are what we do during a write miss. So when we implement a particular cache, we need to choose among these 4 possibilities. Now this design choice of write through and no allocate has a special name. It is called a write around cache scheme. The name comes because when we have a write miss, what we do is we do not allocate. That means we write only the memory location corresponding to the word which was being written by the processor and not any cache entry at all. So we are writing around the cache. That's why this has this special name, write around cache. If you think about it, all these 4 possibilities are certainly possible. However, the ones along the diagonal shown here, these two choices, the write back with no allocate and allocate with write through, are possible but make less sense. This is because if you think about it, in an allocate scheme, the reason why you are allocating is that you want to be lazy about reflecting the writes to a memory location back to the main memory. So allocate makes more sense with the write back scheme than with a write through scheme. Likewise, the write back scheme means that you want to be lazy about writing back onto the main memory. So it makes sense to couple it with a scheme which allocates on a write miss. So to summarize our discussion in this video, we have looked at the direct map caching scheme, which essentially does a many-to-one mapping of memory block number to cache block number. To implement this scheme, the cache, in addition to the block of data, has metadata in terms of tag and a valid bit. And during memory access, the cache controller will break up the memory address into various fields, the last 2 bits being 00 for a word aligned byte address, the next few bits representing the word number in block corresponding to the number of words in a block, and then the next few bits correspond to block number in cache, and this number of bits will depend on the number of blocks in the cache, and the rest of the bits towards the MSB form the tag, which is used for comparison with the tag metadata as part of the cache block. And finally, we also saw that there are 4 possible design choices with respect to the write policy in a cache, 2 of which make more sense than the other 2.